Okay, welcome back to the pre-lecture video segment. We're going to talk about spatial representation and transformation, which we have already gone through part of it in the live lecture. So this video segment will serve as a very quick recap and also a very concise overview of the entire chapter that also include transformation, which we haven't covered in the live discussion. So in the class, we look at what coordinate systems are. We also give definition of the reference frames that are coordinate systems that really help us to describe the position and orientation of a given rigid body with respect to some other rigid body or even a universal coordinate system. Okay, so these are some important concepts that you might have to bear in mind, although they are very straightforward. And so something trivial but worth noting is that when we talk about the pose of an object, we are really talking about the position and orientation. Okay, so it consists of the definition of position and orientation of that particular rigid body. And so we will see that it is actually mathematically equivalent to your transformation, which consists of your translation and your rotation. Okay, so they are like your position and your orientation. And in representing transformation, we're going to look at homogeneous transformation metric to help us systematically operate on these various transformations. So they are mathematical operations that can be done systematically in kinematic analysis or many other multi-body dynamical system that you will come to learn in subsequent chapters. So these are the few important points. A very quick recap, something trivial and what you're already familiar with are examples of coordinate system like Cartesian, spherical, and cylindrical. Okay, so in this course, we're going to use a homogeneous coordinate system to help us mathematically represent um, spatial information, including transformation. Okay, and later on, your projective coordinate in your robot visions. So they are actually related. Okay, in fact, your homogeneous coordinate system is a form of projective coordinates. Okay, so we give formal definition, wanting to recap about this reference frame is that it can be assigned to rigid bodies. Okay, so these are really a coordinate system that help to specify the position and orientation relative to one another. Okay, so you will see all these frame assigned to the rigid body that will help us to describe the pose of this rigid body, okay, with respect to probably a universal coordinate system like O that is considered something absolute and doesn't really change. Right, so when we talk about pose representation, we are really trying to describe the position and orientation, in this case with respect to a frame of reference. Okay, so it is a mathematical representation, and we can actually use vector and metric to represent the position and orientation respectively. All right, so of course there are very different kind of mathematical expression used to represent your orientation especially, and even your position. So um, what will be used extensively in this course is your positional vector and your rotational matrix. Okay, so having said that, I'm sure you already see the relationship between your pose and the transformation. Okay, so transformation, they are kind of like change in pose or reference frame. Okay, so when we change the coordinate system from one to another, it's a transformation operation. Okay, so again, you can use vector for translation and metric for rotation, just like what you have done for your position and orientation. Okay, so we will talk more about the application in class again. And in this course, one thing to note or something that might be new to you is homogeneous coordinates. Of course, you don't have to worry too much for this course as far as we are concerned. It's just about adding a 1 at the bottom of your column vector. Okay, so in a 3D space, you're going to have 3 variables, but in this case, you're going to add in 1 at the bottom. Okay, so instead of a 3 by 1 vector, you're going to look at a 4 by 1 positional vector if you express it in your homogeneous coordinates. Okay, so they are nothing but projection to their principal unit axis. And so when we talk about the orientation of a given frame, we can express it in a metric form. And this metric really consists of 3 important vectors. Okay, so all these 3 vectors are orthogonal. So they are the orthogonal unit vectors or principal unit vectors. Okay, that means if you do a x cross y, you're going to get your z. Okay, and so perhaps this might be trivial to some of you, but uh, if you look at it, how do we express the vector in a coordinate frame, or rather a coordinate system? It is actually projecting that vector onto the principal unit axis of that particular reference frame that we're talking about. So in this case, we are trying to project, say for example, YB onto these 3 uh, unit vectors, these 3 principal unit vectors of frame A. So it is actually a dot product operation. So if you remember your dot product, uh, of course, YB is actually associated with JB. Okay, in this case, YB is just JB. Okay, another way of writing your unit vector, usually we use IJK. Okay, so JB is really your unit vector for this YB direction. Okay, so projecting it onto the 3 principal axes is like doing a dot product. Okay. Right. So if we want to further visualize it, of course, this is something we went through in class already. Just use your trigonometry to write down the vector coordinates. Okay, to write down the position coordinates of this vector, and you will see that it kind of gives you this same metric that you would derive with the vectors. So you can do some of the conceptual tests or check with very obvious rotation like 90 degree to see if it agrees with the geometrically derived expression. Okay, so orientation in 2D is very much the same, or in fact mathematically equivalent to rotation, rotating operation. Okay, so imagine what we have seen earlier on with the orientation in 2D. It is the same as us rotating this frame A in the z direction, in the z-axis, okay, by theta degree, okay, by an angle of theta. All right. So of course, in this case, in this course, in fact, we're going to take the right-hand grid rule convention. Okay. So again, your x cross y will give you your z. Although it's a 2D plane, actually you will see that your z axis is pointing outward. Okay, I'm not writing the dot properly. So of course, pointing inward will be represented by a cross, and pointing outward will be represented by a dot. Okay, so if you use your right hand screw rule, you should be able to see that the z-axis is pointing outward. Okay, counterclockwise is the positive direction. So we denote this operation as r sub z with the parameters of theta, that is the magnitude of rotation. Okay, and z is the direction of rotation. And so your orientation is nothing but a rotation of the coordinate system. Okay, So this part is important to remember. And let's say if we think of it this way, if we want to change the coordinate system, for example, we want to know the point P with respect to our coordinate system A or the reference frame A, but we only have information from an observer that is attached to B. So say there's an observer at B. He's looking at the point P and telling us that this is the coordinate system of point B. But we are interested really in AP. Okay. So what we need to do is to find our relationship with this observer at B. Okay, so imagine if we are someone attached to A. Okay, we need to know our relationship with B, and this is actually a difference in orientation, and so it is represented by ARB, the expression that we have earlier on. Okay, and so this is what we can do, multiplying uh, this rotation operation by our by the coordinate given by this observer. Okay, so that will be a pre-multiplication. Okay, so uh, in this case, it might be quite trivial on how you're going to get your put coordinates in the new reference frame, that is A, instead of using the original observer's uh, coordinate point in B. But if we look at this operation, it is always not, it may not always be so straightforward. Life can be a little bit more challenging sometimes. Say, for example, the origin may not coincide. So the origin of frame A and B may not be the same. And so B is actually an offset away. Okay. And so what we can do is actually to introduce another frame A prime that is having the same orientation as B. Okay, so we are still doing the same operation of rotating in the Z direction. Okay, but after that we still need to add this offset vector. Okay, APB. Okay, so when we do this, this expression here, you don't have to worry about it. It's just for those who want to see how this can be derived. Your basically A prime RB is nothing but identity metric, okay? Because your A prime and your B is actually the same orientation, okay? So that means 1001 is the same axis for both, okay? So what you're going to do here is that you can take this away and you're essentially finding your ARB, okay? So in our textbook, you will see that they represent it this way. Although the notation may be a little bit confusing, ARB, but ARB is really talking about the rotation from A to B. Okay, and so it involves also a summation operation. So not just a product, but also a summation. Okay, so sometimes this can be a little bit inconvenient in doing some mathematical operation. So we want to make a more concise way of doing this. We introduce what we call a homogeneous transformation metric, ATB. Okay, so this ATB, they are basically doing the same operation. Okay, but what you do is to introduce this homogeneous transformation uh, that is a combination of your ARB and your APB. Okay, so how do you do that? If you recall, your R is a 3 by 3 metric. Okay, your P is a 3 by 1 metric. Okay, so this whole thing, okay, is going to be a 3 by 4 metric, right? Okay, so you see that this is a 3 by 4 metric, but the homogeneous transformation metric is a 4 by 4 metric. Okay, it's same row, same number of row and column. Okay, so we like that kind of property. We want something like that, and what we do is to add one more row, one fourth row at the bottom. Okay, so it will be 0, 0, 0, 1. Okay, so now you will have a 4 by 4 metric. Okay, so this is your transformation metric. Okay, so transformation, the chapter or the topic of this transformation will rely a lot of your use in this homogeneous transformation. Okay, so it is just a multiplication. And I will leave you to do some of this concept check to make sure you roughly understand what is going on here. And I will see you in class.